So I think this is problem set 12. And we've got all of our questions set up here, ready to go. So let's go ahead and get started. So for number 1, it says that f of x equals x cubed minus 4 over x. And we want to find all, if any, extreme values of f on the interval from 2 to 4. Okay. And this just means that we want to find all the extreme values there are, if there are any. And yeah, so our extreme values would be our maximum and minimums on that interval. So the first thing that we have to do is take the derivative of f of x. So if I take the derivative there, I know the derivative of x cubed is 3x squared. And then I know the derivative of 1 over x is negative 1 over x squared. And that's just because we're applying our product rule there, really, because 1 over x is the same as x to the negative 1 power. So if I bring my power in front, it's a negative 1 times x, and then I subtract 1 from the power, and it turns into that. So this negative is going to get canceled out. It's going to turn to a plus 4, because that's a constant coefficient, over x squared. So there's our derivative. And the reason we have to take the derivative is because we use this to figure out where our critical points are. And our critical points are typically found by setting the derivative equal to 0, because that means that the rate of change at that point, at the points of x that we solve for, is equal to 0, which means that it is something like this. Like if I've got a function like a parabola, at this point where it's changing from increasing to decreasing, this derivative hits 0 at this exact point here. And so that would be a critical point there, and that's exactly what we're looking for, so that we can figure out on which intervals our function is positive and negative. So if I want to find my critical points, I'm going to have to set this function equal to 0. Oops. So if I set that equal to 0, well, taking a look at this, kind of see that, I think that this is meant to be inclusive. Obviously x can't equal 0, and it wouldn't anyway, because it's not on our interval. But at any point, if we plugged in any values along this interval for our x, I don't think it equals 0 at any of those points. And that's just kind of me looking at this and taking it logically with my prior knowledge and experience of functions. And you could kind of test that out, just kind of play around with stuff, see if you get anything close to 0. But I don't think you would. I think all of this is going to be positive. And so there are no critical points here, so our only points that we end up looking at are the ends of our interval. And since this is inclusive, we're going to go ahead and include both of these. So when I plug in my 2, I'm going to see, is my function increasing or decreasing on this interval? I'm going to plug in something. Actually, I'm going to plug in a 3, because that's right in between here. So if I plug in a 3 to my derivative here, so if I get this, that's going to be 3 times 3 squared plus 4 over 3 squared, which you could solve this out, but all that we really need to focus on is the fact that this is positive, which means that on this interval here, the function is increasing. Okay, which means that it starts at 2, it's going to start right down here, and then it's going to increase all the way up to 4. Or our x equals, right? Be careful not to think of these as our y equals, because we don't actually know the y equals points yet. But we can see clearly that our minimum on this interval is going to be at x equals 2. And our minimum's here. It's going to be x equals 2, and our maximum is going to be when x equals 4. So now we take those values and we plug them back into our original function to figure out what the actual minimum and maximum are, what their y values are. So if I plug in I'll start with the minimum. So if I plug in a 2, that's going to be a 2 cubed, which is 8, minus 4 over 2, which is just 8 minus 2, which is 6. So our minimum is at 2, 6. And then if I plug in the 4, let's see, 4 cubed, 4 squared is 16, 4 cubed is 64, minus 4 over 4, which is just 64 minus 1, or 63. So our maximum is then at 4, 63. And that seems like it makes sense, right? Because we start down here and we work our way all the way up there. And that's all that they're looking for. So we can go ahead and take a look at our next problem, which is a pretty similar one. So this time it says the f of x equals 3/5 x to the 5/3 power. And again, we want to find all of the extreme values, if there are any, on the given interval. This interval is from negative 27 to 27, which is a pretty broad one. So first of all, once again, we're going to take the derivative. And I know I'm going to use my power rule here. I put that in front. 5/3 times 3/5 cancels out. So we just get x to whatever our new power is. So I'm going to subtract 1. So it's going to become a 2/3. And that's our derivative, right? So now if I set that equal to 0 to figure out where our critical points are, well, that's only ever going to equal 0 when x equals 0. So our critical point is x equals 0. So what that means is that we now have two different intervals to look at because x equals 0 is on this interval. So we want to look at, from here and to here. These are now the intervals we want to look at. I want to figure out whether this interval is increasing or decreasing, and the same for this interval here. So let's take a look. Let's see if I plug in any value between negative 27 and 0 to my derivative function to see if it's positive or negative. Let's see what happens there. It's going to be a negative number. Remember that x to the 2/3 power is the same as the cube root of x squared. So let's try a nice easy one that on this interval is -8. So I'm going to plug in a -8. So x equals -8. If I plug that in, that's going to be the cube root of -8, which is then a -2. -2 squared is 4. So on this interval, we are increasing because 4 is positive because we squared that. And then we'll try out our next interval. Right, and this time I'll plug in a positive 8 because that's also in this interval. So x equals 8. Our derivative equals, well, the cube root of 8 is just 2. 2 squared is 4. So this is also 4. This is also increasing. So it doesn't mean a whole lot to us. So what this means is that it's increasing on the entire interval. So it starts down here where x equals -27. It's increasing all the way to x equals 0. And then from there, it continues and increases more all the way up to x equals 27. Which, drawing this out, we can pretty clearly see that our minimum is going to be when x equals -27, right? And our maximum is going to be when x equals a positive 27. Okay, so now we just need to plug those back into our original function to see what the y values are at those points. So let's take that out. Remember our original function, is this right here. And I'm going to rewrite that as a cube root of x to the 5th power. just because that's a little easier for me to process personally. And so now I plug in my negative 27 first. So f of negative 27 is going to be 3/5 times the cube root of negative 27, which is going to be a negative 3 to the 5th power. That's a tricky one. Let's see. I know that 3 to the 3rd is 27. 3 to the 4th is 81. So 3 to the 5th is going to be 243, and this is going to be a negative, so it's going to be 3/5 times negative 243. I multiply that by another 3. That's going to be negative 729 divided by 5. I'm just going to leave it in that fraction form, as an improper fraction there. Or actually, no, I'll go ahead and rewrite that as a mixed number. I think I'm just going to use a calculator for this, just for time's sake. It's going to be 145 and 4/5. Okay, so that's our maximum. Oh, that's our minimum. This should be negative. Oops, there we go. And now we plug in our positive 27 to figure out our maximum. And because we're just plugging in the positive and negative versions of these numbers, what's actually going to happen is we're going to get the exact same thing, but positive. But I will go ahead and still do that for you, just so you can see that more clearly. So 3/5 times the cube root of 27 to the 5th power. The cube root of 27 is going to be 3. Then we have that to the 5th power. We just figured out that 3 to the 5th is 243. This time it's positive, right? Because the cube root of positive 27 is a positive 3. Which then gets us this, which is then this. Ta-da! And that's all that problem is. Moving on to number 3. This is the same type of thing. It's a little bit trickier to work with, though, just because we've got those e's in there. So once again, we want to find all of the extreme values, if there are any, of this function on the given interval. This interval is only from 0 to 1, so there's not a whole lot that we have to worry about. But let's go ahead and take a look-see. We'll take our derivative here. So I know the derivative of e to the x is just itself. And I know the derivative of, and I'm going to use chain rule here, so that the derivative of e to the 3x would be 3e to the 3x. But I've got a 2 in front, so it's going to be 2 times 3e to the 3x. So it's going to be a 6e to the 3x. And that's our derivative. So now, to figure out any of our critical points, we're going to set this equal to 0. And from here, you might be looking at this and wondering, what do I do? Because it's a little intimidating and it's a little hard to process sometimes. I know initially when I tried a problem like this on the homework, I was just kind of staring at the page for a few minutes until it kind of clicked. But what we're going to do here is we're going to actually move this over, because these mean the same thing, right? It's the same number sentence, just written around a little differently, just manipulating our equation. And now we know that if I have some number to the power of x that equals y, I can rewrite this as a log with a base of that b of y equals x. So I'm going to do that here because I've got my b to the power of x, my b is an e, equals our y. Oops. So I'm going to go ahead and write this as log base e, right, because that's our b, of the y equals x. And a log base e we can rewrite as a natural log. I'm going to write it as x equals instead of this equals x. So I'm just going to flip this around really quick and change this to a natural log. Because I could leave it like this, but it's just easier to think of it as a natural log. It's a little less writing. Now, We just found that our critical point is right here, but that's a little difficult to work with. You could leave it like this, except for the fact that there's still an x up there, right? So we need to work it out so that there isn't an x there. So I'm going to keep going, and we're going to use our log rules here. So I know that if I've got multiplication, I can turn that into 2 logs added to each other. So it's the log, a natural log of 6 plus a natural log of e to the 3x, right? Just because of our log rules. And I know right here, since I've got this power, that's the same thing as if I put that in front as multiplication. So I'm going to rewrite that as well. So now I'm going to put my 3x in front, 3x times natural log of e. That's the same thing as this, right, because of our log rules. Well, I know the natural log of e is just 1, because that cancels out. The base e and the inside e cancel out. So I can keep rewriting this. This is a natural log of 6 plus 3x times 1, or just 3x. And now we're kind of home free, right? I see I can just subtract 3x from both sides, which gets me that a negative 2x equals natural log of 6. And then if I divide both sides by negative 2, I get x equals natural log of 6 divided by negative 2. And there's our actual critical point. So I'm going to erase this work now so that we've just got that point. Okay. If it'll let me. Let's try that. There we go. And so now our interval is looking something like this. Okay, so now those are the intervals we want to look at. So the tricky bit now is understanding about how big that is. Oops. So that's that's a bit of a tough piece, but let's think about it. I know obviously natural log of 1 is 0. Anything bigger than that tends to be a pretty long decimal. I'm confident that natural log of 6 is bigger than 1. So I would say that this is a little bit bigger than... Oh, actually, sorry, I made a completely big mistake here. This is a negative number because of that negative 2, which means it's not within this interval at all. It is outside. It's less than 0, so it's not in the interval we're evaluating. So we are still just evaluating within this interval. So all we have to actually figure out is whether or not the function is increasing or decreasing on this interval. And since this interval is inclusive of our bounds, I'm going to go ahead and just plug in, well, I'm going to plug in a 1/2, I think, because that's smack dab in the middle. So I'm plugging that in here because remember we want to see if it's increasing or decreasing. So whether or not our derivative at that point is positive or negative tells us whether or not it's increasing or decreasing, respectively. So our derivative, when x equals 1/2, that's going to be e to the 1/2, right? So that's going to be the square root of e minus now 6 times e to the 3/2, which is, this is definitely going to be bigger than this, right? Because that would be this, because that half there, then cubed, and then times 6. So it's going to be bigger than that no matter what, which means that if we're subtracting this, we're going to get a negative number. So we can see pretty clearly that it is decreasing on this interval. So I wrote a negative sign, but I'm also going to write that it's decreasing, which means that we have x equals 0 and whatever our y equals, and it decreases all the way down to all the way over to when our x equals 1, right? So our maximum is when x equals 0, we just found, and our minimum on this interval is when x equals 1. And then we want to figure out what the actual y value is there. I'm not going to put it as a long decimal. I'm going to just write it in terms of e for simplicity's sake. So let's see, if we plug in a 0 to our original function. Oops, don't do that. Okay, if we plug in a 0, that's going to be e to the power of 0 minus 2e to the 3 times 0, which is just a 0. Again, anything to the power of 0 is just 1, so this is 1 minus 2 times 1, so 1 minus 2 is -1. And now we plug in a 1, to that function, so we get e to the power of 1, which is just e, minus 2 times e to the 3 times 1, which is just e to the 3. And I'm just going to leave it like that. For inputting it on our homework, I would recommend putting into a calculator and writing out that whole decimal rather than trying to format that for the homework. But this is what the answer should be for this one here. Our next problem is similarly tricky, but for different reasons. So it says the range of a particular projectile shot at an angle theta with respect to the x-axis is given by this function on this interval, where v0 is its initial velocity and g equals 9.8. For what value of theta is the maximum range attained? Okay, so this question might look pretty confusing, but all that it's asking, right, this is the function of our range. They're asking at what point do we reach our maximum on this function, which means we just have to take the derivative, find our critical points, and use those to figure out where our maximum and minimums are, and figure out what value our maximum is at. That's all we're looking for. So if I take the derivative here, well, at the derivative of r, I know this. We don't know our initial velocity, so I'm going to have to take the derivative of that with respect to theta, like so. Over g is 9.8, that's going to stay that way. And then times the derivative of cosine 3 theta is going to be, these are chain rules, so we've got our 3 times, and the derivative of cosine is a negative sine 3 theta. Okay, so now you might be wondering what we do with our v0 and our dv0 d theta. The answer is nothing. Quite literally, none of this bit matters. Because all we care about is when the function is going to equal 0. And our function is going to equal 0, or our derivative of our function is going to equal 0 when this sine of 3 theta equals 0. So this whole thing equals 0 when sine of 3 theta equals 0. So now we just have to figure out when sine of 3 theta equals 0. So at what points that is. So sine of 3 theta equals 0. Well, I know that that's going to equal 0 when theta equals 0, because 3 times 0 is 0. And remember, that would be right here. Right? It's these points that our sine equals 0, and it's these 2 points here where it's not. Or, well, it's everywhere else that it's not, obviously, but it's, yeah. So 3 theta equals 0 when theta is 0. 3 theta equals pi when theta is pi over 3. And 3 theta equals 2 pi when theta is 2 pi over 3, and so on. But we're only going to deal with one revolution for right now. So I know that these are any points along there that I could consider my critical points. So we notice that 2 of these are actually the ends of our interval. So what we notice is that we're going to be evaluating from 0 to pi over 3, and then from pi over 3 to 2 pi over 3 to figure out what our maximum is. So now I'm going to plug in some values just to see whether or not this interval is increasing or decreasing, and the same for this one here. So now I'm going to erase some of that there. So, Oh, okay. So now let's see, we've got pi over 4, pi over 6, pi over 3, and then our 2 pi over 3, 3 pi over 4, and 5 pi over 6. And that's all we're going to look at right there, because I don't think that we, or at least for right now. So let's see, what's something between 0 and pi over 3? Well, let's try pi over 6. If I plug in a pi over 6 to this right here, I'm going to get sine of 3 times pi over 6. That's going to be the same as sine of pi over 2, right? Because 3 times pi over 6 is 3 pi over 6, which reduces to pi over 2. And I know that sine here is just 1, which means that our derivative of that function, well, it looks like all of this should be positive, but I've got a negative here, so it's going to be negative right here. It's going to be decreasing on this interval. Okay. Which makes sense, because if we think about our cosine, from here to here, it's getting smaller and smaller. But continuing on, now I'm going to find a value between pi over 3 and 2 pi over 3. So a value right in between there is, I could use pi over 2. And that would get me, if I plug that in, I get sine of 3 theta. Well, our theta is pi over 2, so it's 3 times pi over 2, which is sine of 3 pi over 2, which we know is a negative 1 right down here. And again, I've got this negative here, so that turns into a positive 1. So we're increasing on this interval. And what that means, as I can kind of sketch this out, I've got my x equals 0, and I'm starting at x equals 0, and then I'm decreasing because it's negative on this interval, all the way down to when x equals pi over 3. And then from pi over 3 to 2 pi over 3, I'm increasing to 2 pi over 3. So we see that there are 2 points here where it could be at its maximum, right? This would be really easy if they were asking for a minimum, because that would just be at pi over 3, and I could just put that right there. But they're asking for a maximum, so now we need to figure out which one of these is higher if I were to plug that in. So if I take that into my original function, right, we've got, oh, I never put an equal sign, oops. I've got r of theta equals r v naught squared over g, or over 9.8 in this case, times cosine of 3 theta. Well, if I plug in a 0, it's going to be cosine of 0, right, which is just going to be cosine of 0 is 1, so it's just going to be whatever this is right here. Oh, not of, oh yeah, of 0. And then if I plug in my 2 pi over 3, well, 3 times 2 pi over 3 is going to be 6 pi over 3, which is 2 pi. So that brings me to the exact same point, which means that these are both my maximum on this interval. So that's tough. We might technically be able to write both of these. I don't think the homework asks any questions where there's 2 of the maximums. They would probably be asking for this. But so our maximum range is attained at both of these points. at the end of our interval, and our minimum is at pi over 3, just because of how this worked out. If I'd started off with this being a negative cosine, our maximum would have been that right there. And I probably should have done that to have a better example, but oh well. Let's take a look at our next question, which says that a farmer wants to use 5 miles of fencing to enclose an isosceles triangular region of as large an area as possible. What should the lengths of the sides of the triangle be? And we're using x to be the length of the base of the triangle. So remember that an isosceles triangle is a triangle where it has 2 sides that are equal, and the third may or may not be. In this case, we're assuming that we can't tell, so our base is x, and then these 2 sides are equal. For the moment, I'm going to use s to refer to both of these. So this is what our triangle looks like right now, and he's trying to, make fencing for this whole area here. So first, I know that the perimeter is going to equal 5 miles, right? So I know that all of these sides added up will be 5, so it's going to be x plus 2 times s equals 5. So let's put our s in terms of x. So I'm going to get 2s equals 5 minus x, right? So just move this over. And then s equals 5 minus x over 2. Okay, so that's a good start. Now, we can use that here in just a moment. We first want to find the area of this triangle. So I know the area is 1/2 times the base times the height. We know the base is x, right? But we don't know our height yet, because our height would be right down here. So now we have to use this right here to solve for our height. I know that we'd form a right triangle by cutting that in half, and that right here would be 1/2 x. And our side length up here is what we just found. Okay? So this being our hypotenuse, I know that h squared plus 1/2 x squared, which will just be that, equals whatever this is squared. 5 minus x over 2 squared. Which I can then work out a little bit. Let's see. 5 minus x times 5 minus x, that's going to be a 25 minus 10x plus x squared. So I can rewrite this now as, let's see, expand that out. I've got an x squared minus 10x plus 25 over 2 squared is 4. Now I'm going to move this over there because we want to isolate our h because we're looking for that height. It's going to be this minus, and I could rewrite 1/4 x squared as x squared over 4, which means these are now over the same denominator, which means I can combine these. So I get an x squared minus an x squared. Those are going to cancel. So h squared equals this. And I am going to reduce that because these all have a common factor of 2. So it'll be negative 5x. Oh, no, they don't. 25 does not have a factor of 2. So this is what we've got there. So we've got h squared equals this. Therefore, h equals the square root of this. And that's pretty ugly, but that's what we're going to use. Although, before I go any further with that, I know that 1/4, the square root of 1/4 is 1/2. So I'm actually going to pull this out because this is the same as this bit times 1/4. So I can rewrite my h as the square root of 1/4, which is 1/2, times all of this now. So there we go. That's, I think, the simplest way I can write what our h is. So now I'm going to plug that back into our area. So I'm going to have our area equals 1/2 our base, which is x, times our height, which is a 1/2 square root of negative 10x plus 25. Combine these coefficients, get 1/4 x times that square root. And that is as simple as we can write that. That is the equation for our area. So that's what I'm going to go ahead and plug in. And for this question on the homework, I know we actually do have the like number pad stuff on the side. So you actually can write it exactly like this in the homework for whatever your question is. Okay. So now that we've got that, you might be wondering how we go from there to our actual side lengths. Well, let's see. Let me just clean this up a little bit so we've got space to do the rest. If it'll let me, it's being awfully slow. All right. Okay, so now what we need to find is, well, we know that he wants it to be as large of an area as possible. So we want to know at what point, at what x value is this area going to be at its maximum. And well, we know how to find the maximum of a function because we've just done that a bunch, right? So we're going to take the derivative of this. So our area, the derivative of our area is going to be, well, we have to use the product rule here and a little bit of chain rule because I could rewrite that area as, let's see, I could write it as, I'm going to put the x over the 4 just because that's a little easier to work with. I could rewrite it like this, right? Because that's x times the 1/4, and then all of this to the 1/2 power, which is the square root. And now we use our product rule to take that derivative. So I take our first value, which is x over 4, times the derivative of our second value. Well, I've got chain rule that I need to apply here. So let's say that c equals n to the 1/2. N equals our inside. Derivative of our outside is going to be like this. Derivative of our inside. Oops, forgot to multiply by the derivative inside. That's going to be like that. And so that outside is going to be -10 times 1/2 is a -5. Okay, so that's what that's going to be. So we get times a -5, our inside, to the -1/2. And then it's the derivative of our first term times our second term. So the derivative of x over 4 is just 1/4. So I get 1/4 times that there. Okay. And so that's our derivative. Oops. And it's pretty ugly. It's not a pretty one. Yeah, so now we have to set this equal to 0, which is, let me just double check that I am doing this the way I did it before, just to make sure. Oh yes, okay. So now I'm going to rewrite this. I personally think it's easier to work with square roots if you don't write them as the power like this. So I'm going to rewrite them in that form. So I'm going to x over, well, I'm going to actually take this -5 in front. And I'm going to make it a -5x over 4 times, and this is to the -1/2, so it's going to be underneath, it's going to be down here, square root of this plus 1/4 times the square root of this. And well, I can move those onto the top there, and I can factor out the 1/4, Again, I'm just working with it right now so that it's a little easier to look at, so that we can get a better understanding of what we're working with here, and maybe do some simplifying. Okay, so I see that this is a fraction with this down here, and that's the denominator. And so I'm going to actually give these a common denominator of this, which is going to result like so. And I don't know that all of this is necessary per se, but this is how I did it and how I can best make sense of it. So it's going to be plus this times that denominator is going to cancel out that square root. And now we've got a common denominator. So I can combine like terms, which is going to get me 15x plus 25 over this right here. Okay. And that's our current derivative. So I know that that was a lot, and it's pretty ugly even still. But that's how we're gonna do that. I think I'm gonna factor out a 5 from that. So it's going to turn into a 5 in the front, right? Factor out the 5, bring in front, times negative 3x plus 5 all over that. So now I want this to equal 0, and I want to know when that happens. Well, this is all going to equal 0 if and only if this numerator equals 0 and this denominator doesn't, of course, x would be undefined. So when does a negative 3x plus 5 equal 0? Well, I got negative 3x equals negative 5, 3x equals 5, x equals 5/3, or 1 2/3. So let's take a look. It says our x equals 1 2/3 is what we just found, aka 5/3. And now, well, we know what our other side lengths are in terms of x. So if s equals 5 minus x over 2, it's going to be 5 minus 5/3 over 2, which is going to be 4, 3 1/3, I believe, over 2, right? Because that would be subtract 1 whole, subtract 2/3, good. Which is then, let's see, 10/3 over 2, which is 10/6 or 5/3, and it turns out that they're all the same length. Let's see, if I add them all up, 5/3 plus 5/3 plus 5/3, that's going to be 15/3, which equals 5 miles of fence, which is exactly what we wanted. So that looks correct. Boom. And I know that was a lot, especially this, me trying to simplify our derivative there. So I really hope that that made sense. That was a little convoluted, but I hope that you can make sense of that. Let's take a look at our next one now. So number 6, it says if f of x equals tangent of 7x to the 4th power, then our derivative equals this, where these values are whatever we find them to be. So let's take our derivative. I see that we've got an inside and an outside. So we're going to have to use chain rule here. So our first outside is that 4th power, and then our next outside is the tangent, and then our final inside is the 7x. And then I take the derivatives of them. with respect to each other. Okay, so then I'm going to plug that back in up there, so we get 7 times secant squared of 7x, and I plug that back into our first bit, in which we get 4 times tangent of 7x to the third power times 7 secant squared of 7x. And these are both constant coefficients being multiplied, so it's going to be, so we write our derivative now. We've got 28 tangent cubed 7x times secant squared 7x. Up here, they've just flipped around those, so that's not super important. We see that our A is pretty clearly 28. B is secant to the second. C is a 7, because it's a 7x inside. D is a 3, because it's tangent to the third. And F is another 7. And that shouldn't be new, because that should be practice that we're used to. Let's take a look at number 7. This one should also be one that we're pretty used to. So f of x equals this right here. And we want to find the derivative and then find a tangent line equation for it. So we have to use quotient rule for this. Low d high minus high d low over low low. And so our derivative is going to equal our low term, so 5x minus 1, times the derivative of our high, which is going to be 2, minus our high term, times the derivative of our low, which is 5, all over low low, so the bottom squared. Okay, and now I'm just going to distribute and combine like terms there. So it's going to be 10x minus 2 minus 10x minus 15 all over this here. I see my 10x's cancel out, and I just have a negative 1 minus 15, or a negative 16. Boom. So I can just write that like that. And you should be able to keep the denominator in these terms. And if not, just go ahead and distribute that out, that square. Now, that's our derivative. So we want to find the equation for the tangent line to f when x equals 2. So remember that this is our slope at any given point. So they give us a point, so we have to find the slope at that point. So f prime of 2 is going to be negative 16 over 5 times 2, which is 10, minus 1 squared. So that's negative 16 over 9 squared, which is negative 16 over 81, which is our slope. Okay. I'm going to go ahead and solve for what our y value is when x equals 2 for our actual function. Just because personally I like to put it in point slope form to start. So, and we'll need this anyway. So f of 2 is going to be 2 times 2, which is 4, plus 3 is 7. And then 2 times 5 is 10, minus 1 is 9. So when x equals 2, y equals 7/9. So I could then write it in point slope form, y minus 7/9 equals our slope, right here, times x minus our x value. And now they want it in slope-intercept form, clearly, because they've got a y equals equation set up for us. So what we have to do is move that over and do some distribution. So I'm going to distribute that first, negative 16 over 81x, plus 2 times 16 is 32. And then I'm going to have to add this to both sides to cancel it out. So I'm going to get that. And 7 over 9 is the same as what over 81? 63. So I'm going to get 63 plus 32. So then it turns into y equals, we've got our slope times x, and then combine those, I get a 95 over 81. Which is, I could write that as a mixed number, but I'm not going to for right now. So that should be our equation. I don't expect, however, that you'll have any fractions like this for the actual homework question. So if you do get fractions like that, I would just double check your work. Let's try number 8 now. This one's a little different. This is pretty new. So it says f of x equals 2x cubed minus 6x. We want to find all numbers c in this given interval for which the line tangent to the graph of x is parallel to the line joining these 2 points. Okay, so -3 comma f of -3. Well, let's go ahead and figure out what that point actually is. So if I plug in a -3, I'm going to get 2 times -3 cubed minus 6 times -3. -3 cubed is -27. That's going to be 18, so it gets to be a -54 plus 18, which will be a -40, -36, I believe. So, we know one of those points is -3, -36. And then, do the same thing with our other points. So we've got 0 comma f of 0. If I plug in a 0, both my x's are 0, so that's going to be 0 comma 0. So we want our tangent line to be parallel to whatever line connects these 2 points. Well, we know that for 2 lines to be parallel, they have to have the same slope. So how do we find our traditional slope? Well, I do this right here. Oops. Which in this case is going to be 0 minus a -36 over 0 minus a -3, which is a slope of 12. So we know our slope is 12, which means the slope of our tangent line also has to be 12. Okay. Sorry, I just forgot what the next step was. So now we take our derivative, because when we're finding our slope, normally we take the derivative of a function and then plug in the point that we're evaluating the slope for. So our derivative is going to be 3 times 2 is 6 squared minus 6. Okay. And so now, instead of setting that equal to, instead of plugging in a point there, we're going to set that equal to our current slope, because I know that whatever my x is, when I plug that in, needs to be equal to the slope for the line to be parallel. So now I just solve for whatever my x is here. So it's going to be 6x squared equals 18, x squared equals 3. So our x equals the square root of 3. Or would that be plus or minus the square root of 3? Which, that's obviously 2 points, 2 numbers c. But we have to double check that they're both in that interval. I know that a negative square root of 3 is going to be in that interval because it's going to be less than 2, greater than 1. And it's negative, so it's going to be between here. But a positive square root of 3 is going to be less than 2, greater than 1, and greater than 0 because of that. So only one of these is within our interval. So our answer over here is going to be 1. And now we just have to write what that number c is. And that is our negative square root of 3. The other two don't have answers, so I'm going to say that they don't exist. For the homework, I would put this in as a long decimal, so I'd put that in your calculator and then type that out. But for our sake, I'm just writing it as is. The next one is the exact same question, but a different interval and a different function. So this time, our points here, we've got -3, comma, f of -3. So I'm going to plug in -3 there. Oh, wait. Is that a different function? No, that's barely different. Okay. Sorry. So I plug in a -3. That's going to be a -54 minus 6. Right? Because -3 cubed is -27 times 2 is -54. So that's going to be a -3, comma, -60. Okay. And then our next point is 3, comma, f of 3. So it's going to be 3, comma, we plug in 3. It's going to be a 27 times 2 is 54. 54 minus 6 is 48. Okay, so those are our 2 points now. And again, we have to figure out our slope. So it's just rise over run, right? Which is, let's see, that'll be 48 minus a -60 over 3 minus a -3, which gets us 108 divided by 6. I know 108 divided by 2 is 54. I know 27 divided by 3 is 9, so 54 divided by 3 is going to be 18, I think. So our slope is 18. And once again, we're going to take the derivative of our function. This time it's just 6x squared. And now, once again, we set that equal to our slope to solve for what our x value is. So this is an x squared equals 18, or sorry, 6x squared equals 18, x squared equals 3. Funnily enough, we get the same result for our x, but we have a different interval this time, so we have to go and see if both or any of these two values are within that interval. Let's see, I know a positive square root of 3 is between 1 and 2, which is on this interval, so that checks out. I know a negative square root of 3 is between -1 and -2, which is also on this interval, so that checks out. So this time we have two numbers that exist in this given interval. We want to write them in increasing order, so I'm going to put my -1 first, and then my +1, and the last one does not exist. Okay, we're almost done. I think we just got 3 or 4 questions left. These last ones are a little tricky, or at least a couple of these are. Let's go ahead and take a look at number 10. It says g of x equals this function here. You want to find the slope of the line joining these 2 points. So let's see, this first point is going to be 1, comma, whatever g of 1 is. So if I plug in a 1, that's going to be a 2 times a 1, then minus 3 over 1, just minus 3. So it's going to be 1, comma, -1. And then I plug in my other one. Let's figure out what our other point is. So g of 3, 3 squared is 9, so it's going to be 18 minus 3 over 3 is 1, 17. Okay, so now we find our slope, rise over run. This case is 17 minus a -1, 3 minus 1, that gets us 18 over 2, which is a slope of 9. Now this next bit is a bit different from what we were just doing. Because this is incredibly difficult to actually solve for our zeros, we're going to use the Newton-Raphson method to estimate the values of c where our derivative equals the slope. Okay, so we want to figure out at what points our derivative equals that slope, but we're going to be using our Newton-Raphson method to estimate that. So remember that our Newton-Raphson method says this here. And because of that, we need to know our derivative. Well, either way, we need to know our derivative. So we're going to go ahead and take that derivative there, which is then going to be a 4x plus 3 over x squared. So, all right, so we have our derivative there, and we want to see when that derivative equals our slope, right? So what that means is we're looking at this here, when that equals 9. But our Newton-Raphson method is for estimating zeros. So I need to set this equal to 0, which means I need to move my 9 to the other side, which instead gets me this, which means that this is the function we're going to use for f of c in here. So I'm going to make a note of that. I'm going to write that f of x equals this here, minus 9. And now we need the derivative of that for our Newton-Raphson method. That's going to be 4. That's going to be minus 6 for x cubed. That's that. So now I'm just going to start at either end of my interval and work my way until I get to a point where the, what's the word? Where I get two results that are identical in my calculator. Remember that for homework, we want our calculator to be printing at least 10 digits so that we can get as exact as possible. So in this case, I'm going to start with a 1, I think. So I'm going to say that C1 equals 1. And remember that means C2 is going to be 1 minus f of 1 over f prime of 1. So I'd plug those in there. I'm just going to do this with my calculator though. So let's see. This will take a moment for me to type in, but once I have it typed in, it should be pretty quick. Okay. Oops. And I typed it wrong. Whoopsie. Oh, interesting. So when I plugged that in, I got 0, which means that I can't go any further. So let's try a number other than 1 for our first c value, because I don't think that that's going to work for us, and that might be because our interval is not inclusive. So let's try 2. Let's go smack dab in the middle, see where it takes us. So say c1 is 2, take that function, c2 is then 27/13, c3 is where we start getting big long decimals. Okay, and I'm just gonna keep going until I get an identical one, and that was actually really fast because C4 and C5 are equal, so that is one of our values. Now I'm going to try plugging in another value for our C1 just to see if we get anything different. If we always come back to this same result, then we can safely say that there's only one of these values in that interval. But we do want to play around with it a little bit just to make sure that there aren't more than one. In this case, our C1, I tested out 1.5, C2 is then 2.25, C3 is making its way back to what we just had, so that seems good. Let's try just one more, where C is maybe 2.5. Okay, and that also works its way right back. So we can safely say that only one of these values exists, and that it is this right here. And that the other two do not exist within that interval. All right. Number 11 is a little confusingly worded, but I promise you it's not actually that complicated. We just have to kind of visualize it. So it tells us that the function h is continuous on an interval a to b, and is differentiable on the interval a to b. Suppose that this function, h of x, equals 0 for 5 distinct values of x in that interval. We want to find what is the minimum number, k, of z in our interval a to b such that the derivative of g of z equals 0. And that was a lot. But what that's really asking, if we just look at this question here, that's asking us how many times, like how many different values of z do we have our derivative equal to 0, aka how many critical points are there for this function on that interval. And that is made pretty easy for us because they tell us it's continuous, so we don't have to worry about any holes or jumps or asymptotes or what have you. We don't have to worry about any discontinuities. So I can just kind of sketch this out. It says that our function equals 0 for 5 distinct values, which means it crosses 0 at 1, 2, 3, 4, 5 different values. And for this case, it doesn't matter where those zeros are. It doesn't matter if it does this or if it does this, right? All that matters is that it hits 0 at all those points. Those are all distinct values. And I would just draw it out like this for simplicity's sake. And so we're looking for when our derivative equals 0. Well, that's going to be whenever it's changing from increasing to decreasing, which would be right here, 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 and here. How many is that? 1, 2, 3, 4. Boom. 4 is our answer. There must be at least 4 points where our derivative equals 0 due to this. I hope that that makes sense. Really, all you have to do for a question like that is just draw it out. And for most questions, honestly, visualization helps a lot. Or at least for me it does. And then our last 2 questions are just derivative questions, which shouldn't be too tricky, but I will go through them nonetheless. For this first one, we have to use our quotient rule. So low d high minus high d low over low low. And our first derivative should be in terms of just like that, so it should be fine. So let's go ahead and take that derivative. So it's our low term times our the derivative of our high term, which is 2, minus our high term times the derivative of our low term, which derivative of 3 is 0, derivative of 2 to the x, it's going to be 2 to the x times natural log of 2, and then all over the bottom, our low term, squared. And remember, just in case we forgot, the derivative of any number a to the power of x equals itself times the natural log of whatever that base a is. That also goes for our e to the x, right? We know the derivative of e to the x is itself, but the reason that is because it's this, and the natural log of e is the same as 1, so it's just multiplied by 1. Okay, so I can see pretty clearly, oh, my a is on the other side, but it's a 2 times 3 plus 2 to the x minus a 2x times 2 to the x times the natural log of 2 all over 3 plus 2 to the x to the power of 2. It's funny, they're all 2's. It's crazy. All right, and then our final question says that y equals this, therefore our derivative will end up looking something like this. So this one is just chain rule. So our outside is something to the negative third. Derivative of that would be our power rule. Okay, and then times the derivative of our inside. Our inside is all of this. Oops, not v prime, just the v. And then the derivative of our inside is going to be 9 minus 2 over x squared, which means that our dy dx is going to be, let's see, we get negative 3 times our inside to the negative 4th power, right? And then times the derivative of our inside, which is this over here. And that's exactly the same terms as they have it. So our a is negative 3, b is negative 4, c is a 2, and our d will be to the 1st power, so that's a 1. And that is it. That is all that this homework is. I know some of these were trickier than others, and per usual, I didn't do the greatest job of explaining some of it, but I really hope that you can make sense of everything that I said today, and I hope that this video is helpful. Thank you for watching.